people over there just to comment.
Okay.
Okay, you can. Yeah, I think we can start.
All right. Well, good morning, everyone. Welcome to the presentation by Dr. Ram Hashmonay of OPGAL. Dr. Hashmonay is an international expert in development and implementation of optical remote sensing and other advanced air monitoring methodologies. He's a co-inventor of the radial plume mapping method, EPA test method 10, optical remote sensing for emissions characterization from non-point sources, in projects performed under Dr. Hashmonay's direction for both public and private sector clients. Advanced methods have been used to measure gases and particulate emissions from sources as diverse as landfills, concentrated animal feed operations, wastewater treatment plants, chlor-alkali plants, refueling stations, military aircraft, fugitive dust from military activities, open burning barges, near road mobile sources, agricultural operations, fertilizer manufacturing plants, oil and gas production refineries, coke oven batteries, chemical manufacturing plants, and petroleum refineries. These field experiments provide essential data for calculating emission factors for these sources. His methods are also applied for emergency response, as well as human health and safety applications. Welcome, Dr. Hashmonay.
Good morning. I have a presentation right here this morning, and I have another one at 9:30 in the next room. I'm going to talk about quantification using OGI. But this presentation, we're going to focus on the advantages of changeable hard filter cooled OGI technology for leak detection and quantification. Leak detection is about sensitivity, and towards the end, I will talk a little bit about quantification, how sensitivity is very important to optimize sensitivity by using different filters to get more accurate quantification. So this is the next two slides are talking a little bit about OPGAL, introducing. We are honored to be a lead sponsor today in this conference. And OPGAL is a leading thermal imaging company, world leader, and over 40 years of experience in thermal imaging. And we are owned by Elbit Systems, which is a conglomerate of defense contractors and all kind of companies. So what we do in thermal imaging, we have the defense systems, we have security, we have aviation, we have a system called EVS that help pilots land airplanes in remote fields when they don't have a lot of not big airports, like more rural airports and more remote airports. And we have OEM and open cameras. We sell the cores to other manufacturers, the detector and the electronics. And we have the industrial. Industrial is our division that under this industrial division, we have the optical gas imaging technology, which is, I'm sure everybody knows by now what is optical gas imaging. So I'm going to introduce our optical gas imaging camera, EYECGAG 2.0. It's our second generation. And my talk is essentially on a unique feature that we have. We have a hot filter. We don't have a cold filter. And that gives us the opportunity to optimize detection and quantification by replacing the filters. So this is, I brought here a box. And later, if you come by our booth, I can show you how you replace the filter and optimize it to different compounds. Part of our customers, I paid my due to OPGAL, and let's go to the scientific Conference. So this is a little bit about OGI. We have a thermal camera. It's a cooled camera around 3 to 5 micron mid-wave IR camera. It has a special filter, bandpass filter, that is optimized to the absorption line of the gas of interest, of the target gases. So this is the same of any OGI that has. It's a thermal camera with appropriate filters for detection of the gases. So,
Excuse me, sir. Would you like a quick beer? I know you need to ask about that.
this is,
Just a quick of your presentation?
no, that's fine.
If you want me to hear from this one. Yeah, sure. It's got the USB. Okay, thanks.
So I put a complicated questions and I didn't write all the terms, but this is just to get you an idea. In my next presentation, I will go into terms in more details. It will be more physical physics presentation. Here we have a 2-layer radiative transfer model, and then we derive from, you put in the contrast, the delta I, which is at each pixel, at each wavelength, we get the contrast, which is the radiance difference between the background and the background without the presence of the gas and the background with the presence of the gas. And once we derive it, and we have some terms here, the transmission, this is TA, this is transmission of this layer, which is the atmosphere, and this is the transmission of this layer, which is the gas plume. We have 2 layers. We have the foreground air, and we have the gas plume. And if you can see here, the transmission of the gas plume is a function of the absorption coefficient of the gas. And I want to look at it, you guys to look at it as the absorption coefficient spectrum. It's a function of lambda. It's a full spectrum of the absorption coefficient times the concentration times the width of that plume. You know, LG is the width of that plume. So you can see that this transmission here is a function of concentration and width of the plume. Therefore, gases that has larger absorption coefficient will be easier to detect with this technology. So it's a function of concentration. That's what I wanted to show you, Ryan. So if you look at the fully developed, this is a contrast of the radiance when you have no gas, radiance with the gas. This is the contrast that I talked about. It will be equal to this. And right now we are not talking about as a function of lambda. We are looking at the whole band together. So when I talked about a bandpass filter, you can see here, this is a graph that I put together, the camera filter. This is our standard filter that we use. And 3 gases. I have here methane is the red line. You can see that our standard filter is centered around the methane. And we have here, you can hear me? That's funny. Okay, I'm sorry. And we have propane and butane. So what I want to show you over here, that our standard filter that is very common with all OGI technologies is missing some of the more heavier compounds over here. So if we have an opportunity to replace it in case we are going to a refinery when we don't have methane, it will be better for us to use a filter that is centered around this compound. Then we get better sensitivity and better quantification eventually. So this is the OGI equation, and this is no longer as a function of lambda. This is not spectrum. And then we integrate over the 1 minus the transmission through the gas plume times the transmission of the filter. And this feature is very important. Now, in the portable OGI camera, we essentially assume that the transmission through the air, since we are looking very close to the leak, we are watching very close, the atmosphere is negligible. So that means that we put in this equation, we assume that tau of A equal 1. We drop this. But this is no longer true if we go further away. And when we go further away from the leak, we start considering this. And the atmosphere is starting reducing our signal, the contrast in the camera. And then if we need to optimize our detection for long range, we need to consider other filters. So what OPGAL has? We have a full suite of OGI technologies in the mid-wave IR and long-wave IR. And essentially, this is this is the cooled OGI EYECGAG 2.0. This is the center of our talk today. This is the one that has the replaceable filters. We have the long-wave IR, lower cost, lower sensitivity, much lower sensitivity, just for methane. It's a phone size camera. We call it EYECGAG Mini. On the 24/7, we are now developing 2 cameras, EYECGAG 24/7. This is uncooled camera for methane. And here the EYECGAG 24/7 Pro, the cool camera, essentially for methane and hydrocarbon. It's the same technology as our portable, but it's designed mostly for long range. And it's very important that this camera will have a suitable filter for its application. If we're going to do methane, we may go with a standard filter. If we want to do it in a refinery, that methane is less of an important, we will use another filter. So, and right here, we develop, somebody has his phone over here. You don't want me to read your. Over here, we have the EYECSITE software. This is our portable quantification software that we just developed, and this is the center of my talk at 9:30 in the next room. I'm not going to go much into that right now. So you can read this. These are all the features of our EYECGAG 2, and one of the main features is interchangeable filters. That's why I'm going to talk about it. But it's one thing that I want to say, it's EPA QUADOA compliant, and we have several filters, including a filter for CO2 that we can replace and actually see lower sensitivity CO2, but we can still see with the same camera CO2, not just hydrocarbons and methane. So I think I need to. So this is for people who never saw OGI. So we have a leak here, we have a vent here in somebody's backyard. Over here, this is second you see leaking methane. So anyone interested in our features, please come by the booth and we'll talk to you and explain. Let me move on. This is the EYECGAG Mini. It's if in the other camera we see about 0.35 gram per hour in specific conditions, in the same conditions we can see 10 to 20 gram per hour with these cameras, a fold of 30 to 50 worse sensitivity than the other camera. But we can still see intermediate to big leaks. You can see here in the camera, you can see the leak of the methane, which this one was about 1 kilogram per hour.
Does it just fit on your cell phone?
No.
Or with the whole device?
The whole device, you can come and see it. The whole device is a cell phone and a camera. It's like it's cell phone size camera. Okay. So just to give you an idea, between the two, L we are seeing methane, and if you change the camera, we have 3 cameras, one for SF6 and one for coolants, for refrigerants, using in the long wave, and sensitivity is moderate to high, to low, and this is the range of the LWIR, 7.5 to 14 micron. MWIR is the mid-wave IR is 3 to 5 micron, high sensitivity, and no specificity. It's just VOCs. We cannot tell which one it is. So let me explain what we are looking at. We are looking at the compound. This is our standard filter. So we're looking at, we are not using in our GAL the response factors of the OGI. We are actually look at, since it's not really a factor, it's a curve. It's a curve that is a function of concentration. So it's not a constant that you multiply, and it's relative to propane. Each compound gets its own curve, calibration curve. So we are looking at it in a slightly different way, and we normalize this curve to be calibrated to concentrations, that we can get this curve calibrated to concentration. So this is just demonstration of the integrand. This is the integrand of this. Remember the integrand inside the OGI equation? It has 1 minus the transmission to the gas plume times the transmission of the filter. So if we plot it in different concentration, this is the methane, how it looks, the methane. But if we take the propane, which is on the side of the filter, this is how it fills in, and it's not very optimized. So you can see how it fills in. When we get higher concentration, it fills in and gets saturated. We get no response. Once we get to a certain concentration, we start getting its dynamic range is more limited. If we move this filter to the right, we can get better optimization. It's all about optimization. Where is your absorption coefficient and where is the filter situated? You're trying to optimize detection and quantification by putting the absorption coefficient spectrum inside the filter. When it's better situated, it's better detection. So these are the curves that I was talking about, and this is a function of concentration. What I want to emphasize here, first of all, that it's not linear. First of all, it's not linear, and each compound has a different curve. One is going this way, which is the propane, and one going this way. And let me tell you, this concentration is not, it's a log scale. So it's not as, because as it comes and fill up the filter, as I showed in previous graph, it's each compound is filling it in a different way. So that's the calibration curve. If we measure this CSR, we can calibrate it to concentration when we measure. Okay, so I want to go back. So this is the filter. It takes about 2 minutes. You take out the lens, unscrew the filter and screw it back. You need to do one nuke, one calibration, and it's ready to go on the other filter. So we have 2 filters. I can show it to you later. One is what we call the heavier alkane filter. It's centered around 3.4 micron, and the standard filter that everybody has is centered around 3.3 micron. So this is the blue one is the standard filter, and I told you this is the green one is the alkane filter, and we also call it the long range filter, because look at these blue lines that over here. This is the water vapor in the atmosphere. So what happens when you look at the standard filter? We have a lot of interference of water vapor, and in hot, humid days in Houston, it becomes an issue, and in other places in the world. Only when you get away. In close range, it's negligible, as I said. But if you go further, this is becoming the contrast that you see in the camera between the temperature is diminished almost, and I'll show you anyway. So this is the CSR, for example, for butane on both filters. So you can see here that the one on the alkane filter, same concentration, we have better response on the alkane filters for butane. So this is the alkane filter, this is our standard filter. They're behaving similarly, but we have better sensitivity on the brown curve, which is the alkane filter. This is a concentration 1000 ppm meter, give us larger response in the camera. So that means it's more sensitive. So what I'm showing you right here, if we look at the standard filter with octane, pay attention that we have two things here. We have better sensitivity. This is HEXANE on the standard filter. You can see it, some of it is outside. That's one issue. And then when you start to fill it in, it will get saturated very fast. And you can see the water vapor. But if you go to the other filter, the HEXANE is more centered inside the filter and the water vapor is outside. So we'll get much better contrast in long ranges for detection in long range. And what I'm showing over here, again, this is the long range. So we have twofold advantage here. Better sensitivity, even in close range for the heavier alkanes, but also in long range, everything we can see better. Even the methane that is outside we will see beyond 100 meters, we'll even see methane better because of the contrast. I'll show you it in a second. So this is and you can see the C of the A, the transmission to the atmosphere is a function of the water vapor. So the larger this concentration and the larger the distance, now we cannot look at it as equal to 1. It's much smaller than 1. Sometimes it's going to very small numbers, and then it will be reducing the sensitivity of the camera over long range and for the alkanes. So this is an example. We put two cameras, one with a refinery. On the right is the standard filter. We have like 10 kilometers away, we have a mountain range, not visible over here. We have no gradient of temperature on the sky. This is the horizon sky, which is hotter. The sun is behind us, the horizon, and then the high sky is colder. Over here, we have no gradient. And you can see there is a leak 500 meters away. You can see it with the camera. It's a tank farm. It's a refinery tank farm. You can see the leak going out here. It's you can see it. You see the color over here on the roof? It's probably, you can see the gas, but here, I'll show you a movie in a second. You can see the leak much better, much better. So this is what I mean by changing the filter for long range. We both have better detection for the alkane, short range and long range, but I think in long range, if we have a methane leak, even big one, over here, we will not see it because we don't have much contrast between the background. So this is how the CSR of the alkanes. This is the propane. So these are the same concentration, same colors. You can see, but by the time we get to the gray, we don't see any feature of the propane. This is on the standard filter, but we go over here, the gray one, I don't remember which concentration it is. The gray one is 10,000 ppm meter. We still see the feature. We still have a response here of the octane, and once we lose a response on this 100 ppm meter. But here you can see we are losing the response on the standard filter. So this is the CSR on both filters, and just to comparison for propane. So I'm going to show you alkanes at long range, which is the dual advantages of the alkane filter. You can see this is, I don't know if you can see the movie, you can see the plume. So now you have a big plume coming out of here. You can see the dark, and it's painting it over here. But this is 500 meters away with the alkane filter, and you can see the mountain range that we cannot see, and the gas. We can see the gas with the standard filter over here. The contrast was not good enough. So this is the two advantages. What happened here? Oh, I started over.
It's restarted, yeah.
I want. No. Let's let it finish. Oh, that is slow. Okay, I cannot move the. Oh, I can stop it maybe, and then move.
Hit the arrow twice. See that little arrow at the bottom?
Okay. So this is just now we look at the natural gas, a very long distance, 10 kilometers, like 6.5 miles off a rig. And this is a full day run really fast. You can see the seconds running really fast. We take, so in the morning, the sky is colder. You can see black plume over here, which is black hot. You can see over here. We see a small release. After sunrise, when the background becoming actually warmer, the background of the horizon, we can see this is an absorption. An absorption, that's white. This is a colder plume. And then in the afternoon, we still have a warm spectrum. And what happens here, this is that's when they really crank it up. At 16:45, there was sunset. This is winter. There was sunset, and the sky got cold much faster, and the plume disappeared. This huge plume disappeared because we didn't have any delta T. And you can see 6:45, the plume disappeared, and then after we gave a look, it flipped the polarities. It flipped the polarities because now the sky is colder than the plume. So you can see this is a good demonstration. And by the way, this is methane, and with the long range filter, with the other filter, and we couldn't see this kind of contrast with the standard filter. We measure methane long range with the filters that it optimized for the methane. Okay, I think this is over. So the last value of getting better detection is when we do quantification, we are trying to quantify concentration with the OGI camera. That's the basic of quantification. First, we quantify the concentration, and then we integrate concentration, and we add the wind flow, and then we get the mass flow rate in gram per hour, cubic feet per minute, whatever the units are, but the basic is getting better optimized concentration. So we have developed this EYECSITE quantification. This is a movie. So once a person detects a leak with the EYECSITE EYECGAG 2.0, detecting a leak. I'm showing that this is just the procedure. You take out the camera, the tablet, you connect it wirelessly to the computer, and in 1 minute after you put the camera on the tripod and aim it to the leak, you can get the value of the quantification. But what I want to talk about it, I will give a full presentation this in 9:30. But the reason I'm showing you this is because when we do quantification, we are really starving for sensitivity. And if we want to quantify alkanes, like I talked, not methane, but alkanes, it's recommended to get better factors to concentrations by using the other filter. We get better sensitivity, so we can more accurately quantify when we get very close to our detection limits, either by the environmental conditions or by a small leak. So we better quantify small leaks in worse environmental conditions only by flipping the filter. And we could right now we have the factors only for the standard filter, but we can add the factors, the CSR calibration factors, curves, not factors, curves into this once you replace your filter. And if you want to see the EYECSITE, you can come to our booth, and I have a summary. How I'm doing this time?
Yeah, you're doing good.
Yeah.
7 minutes.
Okay, I'm almost at the last. This is a summary. Okay, what we can see here, we have the 3 filters that we can use. Let me show you. The blue one is the standard filter that is centered around methane, all of these compounds. We have octane and propane here. So we can all detect from close range these 3 compounds. That's why we chose the standard for the portable camera. The alkane filter, the long range filter, is the green one, and it's in close range, it's better detect the heavier alkanes because it's more center. You see the heavier alkanes, but it's getting away from the water vapor. So in long range, it will see anything better. Also the methane, it will see better, even though the methane is almost outside the green filter. In long range, it's better to use it also for the methane because the water vapor is really killing the signal, the contrast signal. And I promise you, the CO2 is sitting over here. This is a CO2 line, and it's on the edge of our detector. That's why our sensitivity for CO2, we have a dedicated camera for CO2 and CO, but we can, if we replace and put a filter of CO2 over here, we can see CO2 in diminished sensitivity, but for some application, it's good enough. Okay, so this is a summary. Thank you, and I will welcome any question. And please come see us at our booth. We can have discussions about all of this. I know it's a little bit too much for in the morning to get. Thank you very much.